Hello students, last session we have discussed about preparation of lyophobic colloids by chemical method, Burdick's arc method, peptidization method. We also discussed about the purification of colloids, that is removing the true solute particles from the colloidal medium. So in that we have discussed about filtration, we have discussed about dialysis, electrodialysis as well as ultrafiltration technique. In dialysis and electrodialysis we have used parchment membrane bag for filtration, whereas in case of ultrafiltration we are using ultrafilter membrane. Now what is this ultrafilter membrane? Ultrafilter membrane is made out of normal filter paper. How? We have to dip the normal filter paper in a collodion solution. What is collodion solution? So collodion solution is actually 4% cellulose nitrate mixed with alcohol and ether medium. So you are taking normal filter paper, you are dipping in a collodion solution, that is which contains 4% cellulose nitrate in alcohol ether medium. Then that dipped filter paper is then added to formaldehyde solution for hardening and kept it for drying. Such membrane is used in case of ultrafiltration technique, and after that we are applying pressure to remove the true solute particles from solution. Now in today's class we shall discuss about some characteristic properties of colloidal particles. So in that, first one is Tyndall effect. Now by definition, Tyndall effect can be defined as it is a phenomenon of scattering of light rays by colloidal particles, which means when light rays are passed through a colloidal medium, it gets scattered. So scattering of light by colloidal particles are termed as Tyndall effect, and this effect is observed only if this effect, that is Tyndall effect, is observed only if the diameter of colloidal particle should be very close to the wavelength of the light. As you know that diameter of colloidal particle should be within the range of 1 nanometer to 1000 nanometer. So those light rays which falls in this nanometer can undergo scattering by colloidal particles. And not only that, this Tyndall effect is observed if, or it can be seen that the intensity of scattered rays, the intensity of scattered rays also depends on the wavelength of the light as well as the refractive index of dispersion medium and dispersed phase. Is it clear? So Tyndall effect is observed if the diameter of colloidal particles should be close to wavelength of light, and intensity of scattered light depends on the wavelength of the light used as well as the refractive index of dispersed phase and dispersion medium. So here you can see the scattering of visible light by colloidal particles. So in this picture over here, when flashlight is passed through the first beaker containing a solution, it can be a salt solution, sugar solution or anything, the path of light is not visible. Whereas in second picture, when flashlight is passed, the path of light is visible because in the beaker we are having a colloidal solution. So this is what we call it as a Tyndall effect. Wow, what is this? What do you see here? So this is seen in nature, a Tyndall effects example where you can clearly see in the nature by itself. So in this dense forest, you can see a dense forest over here, and the sun rays are penetrating into the forest. The path of sun rays are clearly visible like this because of the presence of colloidal particles in the air medium. Those particles can be either dust or water droplets, anything, but it was in the range of 1 nanometer, 1000 nanometer. Because of the presence of these particles, the path of sun rays entering in this dense forest are clearly visible. So this is a Tyndall effect seen in the nature. Yeah, here is another which is also seen in the nature. This is near the sea level. So because of the clouds, the sun rays are trying to enter and you can see the path of light visible. Now see the third effect. This is picturized in a dark room. In a dark room where we have got one glass window and the sun rays are entering to the glass window. So you might also have observed this or might have experienced this. But if you have seen clearly or if you have observed clearly this phenomenon, as the light enters into a dark room, you can also see some particles are moving here and there. That is, the dust particles are moving in the ray of light. So that is the next property of our colloidal particles, that is the kinetic motion. The colloidal particles are not standing still in the medium, it is moving here and there. That movement, that zigzag movement of colloidal particles is termed as Brownian motion. So Brownian motion arises due to the uneven distribution of collision between the colloidal particles and solvent molecules. So solvent molecules, when hit the colloidal particles, it will be moving here and there, dangling here and there in an uneven manner. It's a zigzag motion. And this Brownian motion is observed more if your particles are very small. That means near to 1 or 2, 3 nanometers. And this Brownian motion is less if your dispersion medium is of high viscous. So in viscous medium, the movement is not so much visible. So here you can see in this picture, here the colloidal particles are being hit by the solvent molecules. When they hit, they will undergo this zigzag movement. We call it as Brownian motion, which is being named after its discoverer. This has been first discovered by a British botanist, Robert Brown. He was actually doing experiment with pollen grains. So when he observed through microscope, he was shocked to see that when pollen grains are dropped in a glass of water, when pollen grains were dropped in a glass of water, instead of settling down, these particles are dancing in the medium. They are dangling here and there. He was so surprised to see how is it possible. Then he studied properly and understood that it was because the pollen grains were in the size of colloidal range. Hence, those particles in the colloidal range, that is 1 nanometer, 1000 nanometer, these colloidal particles are not standing still in the medium. They are having a zigzag random motion in the medium, which is termed as Brownian motion. So the optical property is Tyndall effect, the kinetic property is Brownian motion by colloidal particle. Now the third property which I would like to discuss here is the charge on the colloidal particles. It is very interesting to note that each and every colloidal particles will either possess either positive charge or negative charge. So to give an example of a positively charged colloids, what we can say, for example, hemoglobin. Hemoglobin is an example of positively charged colloids. Similarly, hydroxides of metal, aluminum hydroxide sol, ferric hydroxide sols, all these hydroxides of metals belong to positive charged colloids. Whereas negative charged colloids, example to say starch solution. Starch is an example of negatively charged sol. Similarly, gold sol, platinum sol, all metal sols comes under negatively charged colloids. Now, can you just think how these colloidal particles are possessing the charge? So let us answer this question. Colloidal particles gets charges in either of these methods. First, electron capture by the particles during electron dispersion of metals. Second, preferential adsorption of ions from solution. Third, formulation of electrical double layer. So the first method, electron capture by the particles. So this happens during Burdick's arc method of preparing lyophobic colloids. Hope you remember that method, or I will explain once again. So in Burdick's arc method, we are taking two metal electrodes whose soul has to be prepared, and they are dipped in the dispersion medium, and the two electrodes are connected to high electric discharge. When high current is passed, they start vaporizing. This beaker is immersed in a trough containing ice bath. So these cations, which is discharged from the electrodes, are cooled and will be kept in the dispersion medium of colloidal range. So these particles will attract the mobile electrons. So the loosely bound electrons of these cations get absorbed on the layer, thus giving a negative charge to the colloidal particles. So that is how electron capture method will give a negative sign to the colloidal particles. Now the second method, preferential adsorption of ions of solution. This usually happens in case of peptization method of preparing lyophobic colloids. That is, when a medium contains an ion common to the colloidal particles, adsorption of ions takes place. Now let me explain. So we have discussed this already in the peptization technique. So converting a precipitate into colloidal range. For example, when you have silver iodide precipitate, to which when you add silver nitrate AgNO3, the common ion is silver ion. This silver ion will adsorb on the surface of this silver iodide and creating or giving it a positive charge. Now this colloid is having positive charge. It is because we have added a peptizing agent, silver nitrate, in which silver is a common ion. But silver iodide salt can be converted to negatively charged particle also. How? For the silver iodide, if we are adding potassium iodide as a particle, if peptizing agent potassium iodide is added, now which is a common ion here? I minus, iodide ion. This iodide ion will adsorb on the surface of this silver iodide, adsorption of the silver iodide, giving it a negatively charged touch. So a precipitate is converted into a colloidal form by the adsorption of the common ion present in it. Similarly, next example, in case here, if a ferric chloride is added to hot water, we are going to get hydrated ferric oxide salt, which is positive in charge. Second example, if ferric chloride is added to hot water, we get hydrated ferric oxide salt, which is positive in charge. How we get positive charge? It is because of the adsorption of ferric ion, Fe3 plus ion on the surface. So to hydrated ferric oxide, Fe3 plus ion, ferric ion get adsorbed, giving it a positive charge. But in same example, in same case, we can convert this into negatively charged colloids. How? If ferric chloride is added to sodium hydroxide solution, if ferric chloride added to sodium hydroxide solution, we will get hydrated ferric oxide salt, but it is negative in charge. That is because the hydroxyl ion, OH minus ion present here, will adsorb on its surface. So we get a negatively charged hydrated ferric oxide salt if ferric chloride is added to sodium hydroxide. So hydrated ferric oxide is adsorbed or surrounded by OH minus ion. This is what we call it as a preferential adsorption of ions. Now the third method, formulation of electrical double layer. How is this double layer formed? To explain this, let us go back to our previous example. Sir. Now, this is our previous example, preferential adsorption. Now here for silver iodide, silver ions are getting adsorbed. Now this silver ions can attract the counter ion which is present in the solution. Which is a counter ion? Nitrate. So this silver ion once attract the nitrate ion, NO3 minus. Now this is getting adsorbed on it, giving this colloidal particles a negative charge. So we are having here first layer. This first layer is surrounded by the second layer. This second layer is known as Helmholtz electrical double layer. Now this particle is having negative charge. So this formation is known as Helmholtz electrical double layer. Similarly over here also, this iodide ion when attract the potassium ions around it, we will get a positively charged colloidal particle. This is known as formulation of electrical double layer. Helmholtz electrical double layer is formed. Now once when this double layer is formed over here, there will be a potential difference. So once a double layer is formed, there will be a potential difference between the first layer and the second layer. That potential difference between the first layer and the second layer is known as zeta potential. Zeta potential or electrokinetic potential. So the potential difference between the adsorbed first layer and the attracted counter ion is known as zeta potential or electrokinetic potential. So we shall repeat. The negative or positive charge around the colloidal particles will attract the counter ions, forming a second layer. The combination of two layers around the colloidal particles is termed as Helmholtz electrical double layer. And the potential difference between the fixed first layer and the diffused second layer of opposite charge around the colloidal particle is termed as zeta potential or electrokinetic potential. Okay. So from there we are going now to discuss about this properties, electrical properties of colloids. As we have discussed that all colloidal particles will possess either positive charge or negative charge. Hence, they will exhibit electrophoresis mode. So what is electrophoresis? So electrophoresis is defined as the movement of colloidal particles to the oppositely charged electrode when it is kept under electric field. That is, if your colloidal particle is positive in charge and if that colloidal particle is subjected to an electric field, obviously your positively charged colloidal particles get attracted towards negative electrode, that is cathode. So all the particles will be moving towards the negative electrode, which is known as electrophoresis. So electrophoresis is defined as the movement of colloidal particles to the oppositely charged electrode when subjected to electric field. Now here in this picture you can see the solution is taken a U-tube through the reservoir. We are adding, so what soul is taken here. Now here, once when you pass electric current, you have got anode here and you have got cathode here, and you can see that these particles, the colloidal particles, are getting attracted towards cathode. That indicates that once it is going towards cathode, it indicates that it is of negatively charged particles. See, in this picture also you can see here. So before electrophoresis, the particles are distributed in the medium. It is having a Brownian motion moving here and there. But once you apply the electric potential, what happens? The colloidal particles get attracted towards any one of the electrode depending on the charge. So positive particles will move towards negative electrode and negatively charged particles will move towards positive electrode. This movement of colloidal particle is termed as electrophoresis. But now, if by some method, if I stop this electrophoresis, that means when supplying electric current to the medium, I am not allowing the particles to move towards the electrode. I am stopping electrophoresis. That is, the movement of colloidal particle towards the oppositely charged electrode is restricted by using a membrane or by any method. You restrict the motion. Then what happens? Yes. Then what happens is that in such a situation, the particles in the dispersion medium, that is the medium particle, that is a solvent molecule, will start moving towards the oppositely charged electrode. That motion is known as electro osmosis. Is it clear? That is the movement of dispersion medium, our solvent molecules, in an electric field by preventing the movement of colloidal particles by using a suitable membrane is termed as electro osmosis. So electro osmosis is termed as movement of dispersion medium when you stop electrophoresis. That means electrophoresis is prevented. What is electrophoresis? The movement of colloidal particles in the electric field. So once that is prevented, electro osmosis will happen. That is the movement of dispersion medium particles will happen. Yes. Now let us discuss about how to destroy a colloid. As we have discussed earlier, lyophobic colloids are highly unstable. To prepare lyophobic colloid itself, we have to go for many chemical method or Burdick-Sark method, peptidization method, and many artificial methods. Indirect methods are opted. Hence, how do you destroy a colloid? So destroying a colloid is termed as coagulation or precipitation. See, the process of settling down of colloidal particles is called coagulation or precipitation. It can be carried out in any of these methods. That is, you can coagulate or precipitate the lyophobic salts by adopting any of these 5 methods. First one is electrophoresis. Just now we have discussed electrophoresis. That is the movement of particles towards the oppositely charged electrodes in presence of electric field. By mixing two oppositely charged soul, second method. So how is it possible? You have to take a colloid of positively charged and take a colloid of negatively charged. Mix both. When these two oppositely charged colloids come close to each other, neutralization happens, salt is formed, they settle down. Thus, by mixing two oppositely charged salts, we can coagulate the colloids. Third method, by boiling. So continuous boiling of particles, they will bombard with each other, collide with each other, and there is a chance for to settle down. So fourth method, by persistent dialysis, continuously subjecting our colloids to the dialysis technique, the particles of the colloids will coagulate, will join together, aggregate and settle to form a precipitate. The fifth method is by addition of an electrolyte. That is, if you add an electrolyte to a colloids, that is oppositely charged electrolyte to a colloid, results in coagulation. Now this is very important for us to know. What kind of electrolyte can be used? How much amount to be used for this coagulation to happen? So all these are very important, not only for a theory purpose but also for your competitive exams. That is what we are going to discuss next is flocculation value, which is a clear indication of the capacity of the coagulating power of the electrolyte. So let us define. The coagulating power of an electrolyte is usually expressed in terms of flocculating value, which is defined as the minimum concentration in millimoles per liter. How much minimum concentration of electrolyte is added to the colloids for the coagulation to happen. So that is known as flocculation value. So smaller the flocculation value, that means minimum amount we are adding, higher is its coagulating power. So coagulating power of an electrolyte is inversely related to flocculation value. An electrolyte with smaller flocculation value means higher is its coagulating power, which indicates very less amount is required. So you should clearly know the relation and the concept correctly for the CET and NEET exams. So let us discuss how can we understand whether flocculating power is less or not. It is explained with the help of Hareesh-Schulz rule. So Hareesh-Schulz rule states that larger the valency of coagulating ion, greater is its precipitating power. So if you are having an electron with higher valency, their coagulating power is very, very high. For example, it is given here. For coagulating a negatively charged particle, the coagulating power increases in the order. So from sodium, it's Na plus, single charge. Magnesium is double charge, aluminum is triple charge, and tin is raised to 4 times. 4 plus. So 4 plus tin ion or stannous ion is having a greater coagulating power. Now when greater coagulating power means, what will be its flocculation value? That is what you should understand for the competitive exam. So flocculation value is inversely related. They will be having less flocculation value. So increasing in this order, so according to Hareesh-Schulz rule, the coagulating power increases with the valency. Hence, tin ion is having more coagulating power. Now we have already discussed that when coagulating power increases, what is the flocculation value? Flocculation value will be minimum, less. So this is the increasing order of the coagulating power. Now how to write the increasing order of the flocculation value? So in flocculation value increasing order means for SN4 plus the flocculation value will be minimum for this case. Then comes Al3 plus, then for Mg2 plus, finally for sodium. For sodium, coagulating power is less because of one positive charge, hence the flocculation value will be high. More amount is required for coagulating a colloid. So these are the concepts you should be very much thorough with, the relation of flocculation value, coagulating power, and the Hareesh-Schulz rule. So Hareesh-Schulz rule states that the coagulating power increases when valency of the electrolyte increases. So till now we have discussed about the coagulation of lyophobic colloids. 5 methods we have discussed of coagulation. One is by electrophoresis, adding 2 oppositely charged salts. Boiling method we discussed, continuous dialysis method, and addition of electrolyte. All these are connected with lyophobic salts. What about lyophilic salts? As you all know that in case of lyophilic salts, there is a great affinity between dispersive phase and dispersion medium. Hence they are highly stable and it can be prepared by direct method. So to separate this both is a little bit difficult. But still we can coagulate lyophilic salt also. Lyophilic salts can be coagulated either by adding an electrolyte or by adding a solvent. That is, we are changing the medium also. Lyophilic colloids too gets coagulated. Yes. Now we are coming to discuss about the protective action of colloids. So protective action of lyophilic colloids, which indicates that lyophobic colloids are protected from coagulating with the help of lyophilic colloids. So lyophobic colloids will get coagulated if you add an electrolyte to it. To avoid that coagulation, we are adding lyophilic colloid, which will protect lyophobic colloid. Is it clear? So lyophilic colloids are protecting lyophobic colloids from coagulation even after adding an electrolyte to it. See, let us discuss with an example. Here we are having gold sol. So gold sol is negatively charged colloid, to which when you add electrolyte sodium chloride, sodium ions will precipitate, will go absorb on the gold and discharge sol particles. They get neutralized and aggregation or precipitation of particles happen. But to same gold sol, if you add a gelatin, gelatin is a lyophilic colloid. When lyophilic colloid gelatin is added to gold sol, gelatin will cover the gold sol and form a layer around it and prevent this electrolyte sodium chloride to come near and neutralize it. Hence, no precipitation will happen. This is how the gold sol is protected by the help of lyophilic colloid gelatin. Clear? So from here, now we are going to discuss one important concept which is not there in NCERT syllabus, but it is very, very important for a competitive exams. That is about gold number. So what is gold number? Gold number is usually connected with the protective colloids. Now which colloid is acting as a protective colloid? Lyophilic colloids. So gold number is associated with lyophilic colloids. Let us define what is gold number. So gold number is defined as the number of milligram, that is number of milligrams of protective colloids required to prevent the coagulation of 10 ml of gold sol from coagulating after adding 1 ml 10% sodium chloride solution. I shall repeat once again. You are having here 10 ml gold sol. Okay? When you add 1 ml 10% sodium chloride solution, obviously it gets coagulated. To prevent this coagulation, how many milligrams of colloid, lyophilic colloid is added? How many milligram of lyophilic colloids are added? That is termed as gold number. So gold number is usually connected with the lyophilic colloids. So smaller the gold number, greater is its protective action. That means it is much more capable for protecting the gold sol from coagulation. So I shall repeat, gold number is defined as how many milligrams, number of milligrams of protective colloids added to 10 ml of gold sol to prevent it from coagulation after adding 1 ml 10% sodium chloride solution. So they can ask in the competitive exams. And there is a formula to calculate the gold number of colloids. Gold number is equal to number of milligram of lyophilic colloids divided by volume of the sol, that is our lyophobic sol, multiplied with 10. Why 10? Because the standard solution is 10. So this is a formula you can calculate the gold number of any lyophilic colloids. Suppose a question is asked. To a 100 ml gold sol, 20 milligram of gelatin is added. What is the gold number? So you are having 100 ml lyophobic sol. To this 100 ml lyophobic sol, how many milligrams of lyophilic sol is added? 20 milligram. So 20 milligram added to 100 ml. What is the gold number? The gold number you can define as number of milligram, 20 by 100 into 10. So when you cancel, you will be getting 2. Gold number is 2. So gold number 2 indicates that 20 gram has been added to 100 ml solution. So smaller the gold number, greater is its protective action. Very, very important concept for competitive exams. The gold number concept. Hope it is clear. Now we are moving on to another type of colloidal system known as emulsion. So emulsion is a colloidal system in which liquid dispersion phase is immersed in dispersion liquid medium. So both are liquid. Liquid is dispersed phase, liquid is dispersion medium. Liquid in liquid. That is through heterogeneous mixture. You cannot take homogeneous liquids and mix. Okay, so we have got two type of emulsion. One is oil in water emulsion. The oil is a dispersed phase and water is a dispersion medium. O bar W. This is the picture. So here yellow particles are the oil and blue is water. Oil in water type. And we have got second type, water in oil. So water is the particles, dispersed phase, and oil is a dispersion medium. So two type of emulsions are there. O bar W, that is oil in water. Second one is W bar O, water in oil. So oil dispersed in water. They are highly unstable emulsions, hence an emulsifying agents added to such mediums are proteins, gum, soap, etc. because they form a coating around it and prevent it from separating into two layers. So example of oil in water type is milk, vanishing cream, etc. So oil is a dispersed phase and water is a dispersion medium. And the agents, emulsifying agents added are soap, gum and proteins to prevent the coagulation. Then we have got water in oil type. So water is a dispersed phase, oil is a dispersion medium, and here the emulsifying agents added are long fatty acids, alcohols, lamp black, etc. So these are the emulsifying agents added for the case water in oil type. But whatever it is, the emulsions can be broken by heating or freezing or by centrifuging. We can separate these two into two different layers if emulsions undergo any of these processes. So now we are coming to a last part of this topic. Colloid around us. You will be very much interesting to hear that around us there are n number of colloids, and if you go through if you stand in nature and see around you, you are being surrounded with colloidal medium or colloidal properties. So let us discuss few among them. One is blue color of the sky. So sky appears to be blue in color. Why for us? Because of the dispersion of particle light. How is light getting scattered? Because of the presence of particles which are in the colloidal range over there. That is why the blue light is falling into our eye. Next, fog, mist, rain. All these particles are formed because of the colloids. So these particles, that is water droplets, are in the colloidal range in the case of fog or in case of mist or in case of rain. For rain droplets are formed when all the water droplets get joined together to form a heavy clouds. Then food articles. So many of your favorite food are in colloidal medium. For example, jam, jelly, butter, you take chocolate cream, whipping cream, all those things food around us are in the colloidal medium. Blood. So blood is also an example of colloids. In blood, albinoid is the dispersed phase in the medium. And see, when you have a cut in your hand, after a few seconds you can see that it gets clotted. How it gets clotted? Because blood is a colloidal medium, it undergoes coagulation by the reaction, and hence clotting of the blood is possible. Then comes the last, which is known as formation of delta. So formation of delta is also a colloid which is around us. So what is a delta, or how a delta is formed? Let us discuss that. See, river water is a colloidal solution of many negatively charged clay particles. So when river water come and meet the sea water contains many electrolytes. So the river water carries all negatively charged colloidal particles like clay, gravel, etc. And when they come in contact with the sea, which is having electrolyte, coagulation happens, and that settle down in the formation of delta. See from this picture. So the river waters coming from different sources ultimately meet the sea. River water carries all negatively charged particles. When they meet the positively electrolytes of C, coagulation happens, and this is a delta formation which contains sand, gravel, all those things. That is how deltas are formed. See, these are many examples around you which are colloids. So they have got medicines, you have got glue, ice creams, all these are different colloidal medium. Last, the application of colloids. So in application of colloids, the first one is electrical precipitation of smoke. So from the factories, the smoke that is released out will contain so many harmful particles. But if the particles are in the range of colloids, we can coagulate those particles, or we can collect those particles by electrophoresis technique. The smoke is passed into a big chimneys, where a huge chimneys where it is connected to the electric plates. So these electric plates will attract the colloidal particles towards it and will release the smoke with less harmful gases. Then purification of drinking water. So to drinking water, you add a coagulating agent to it. It coagulates or precipitates all the particles, settle down. For example, alum, potash alum is added. It collects all the muddy water and forces it to settle down, and thus forming a clear water on the top. Then preparation of colloidal medicines. Colloidal medicines, that is medicines in the colloidal forms, are very effective for our body. That is why always you can see that in the medicinal bottle they say shake well before use, so that if it is in the pure colloidal form, very effective. Then in cleaning action of soap, which we have already discussed previously in this chapter. Then in rubber industry, so rubber, from the rubber plant you get the latex which is coagulated and then made into sheets. Then in tanning industries, that is in the leather industries and all, which is positively charged animal hide and soaked in tannin, which is negatively charged, mutual coagulation happens and gives the softening nature of leather. So there are so many number of industries which apply the colloidal techniques for making their product much smooth and eco-friendly for us. So these are the examples we can see pictures. So this is a corporal smoke precipitator. When smoke is passed through it, we are having high voltage electrode. So all the particles get collected to this electrode, and the gas free from carbon particles will come out. So this is how we can purify the smoke released from factories. And here is an example of coagulation or purifying drinking water. So to muddy water, you add coagulating agent. Electrolytes are added. It results in the coagulation. So the mud water will settle down, and the supernated liquid is good for drinking. So these are the examples where we are using colloids around us. So with this, the chapter gets completed.